We present MESA, an algorithm for safe reinforcement learning, which quickly adapts and transfers learned safety between different environments. Safety is critical to reliably deploy reinforcement learning algorithms on real-life robotics. However, to learn about safety, the agent must encounter a large amount of constraint violating states. A plethora of recent work introduced risk measures, or a safety critic, to measure the probability of an agent violating constraints. This risk measure is used to help guide an agent to safely learn. However, learning such risk measures requires a significant amount of violations. Motivated by many industry applications, we can minimize the number of violations during data collection in a new environment by leveraging a learned prior from previous interactions of similar environments. This is modeled as N training datasets, where the goal is to learn a risk measure that can quickly adapt to the new test environment. To do so, we propose MESA, a meta-reinforcement learning algorithm that meta-learns the safety critic across the training datasets in phase 1. In phase 2, the meta-learned safety critic adapts to the safety boundaries of the new test environment with a very small test dataset, usually 10 to 100 times smaller than prior methods. Learning such a prior will pave a way for safe learning in phase 3, where the agent directly learns in the new test environment. For our evaluation, we test MESA on 5 different environments. In Navigation 1 and Navigation 2, both testing and training environments vary in the underlying transition dynamics. For cart pole length, the environments vary via the length of the cart pole. Lastly, for half cheetah and ant disabled, the environments vary based on the index of the joint that is disabled. We seek to answer 2 questions. First, can MESA safely adapt into new test environments? And second, how small can the test task dataset be until we observe performance drops? The most important baseline is multitask reinforcement learning, which jointly trains across all training datasets for the safety critic. For both navigation environments, we observe little improvements over that of multitask learning. This is because the environment dynamics between different tasks are too similar. However, for environments where the task distribution results in more diverse and further unobserved changes in dynamics, MESA violates a lot less constraints than multitask learning, as shown in half cheetah and ant disabled. Our results also show that the dataset used for adaptation can be very small and only need about 10 episodes of data collection for the test dataset size. In summary, we present MESA, a new reinforcement learning algorithm that can rapidly adapt safety measures to new test environments with minimal data, outperforming prior approaches for learning safety. Thank you.